Like, what am I doing with the point? Making the y negative. So if this is at positive 2, a would be at negative 2 now. If b is at positive 6, it'll be at negative 6 now. And if c is at positive 7, it'll be at, shh, guys, stop talking. All right. And then we translate. How do you read the arrow notation? What's it actually saying? Right 8, up 1. So if I go right 1, 2, 3, 4, 5, 6, 7, 8, up 1, I end up here. And that's how I end up for all of these. Good. Now, here's my question to you. Based off your findings of like testing the different orders, does order of transformations matter?
Yes.
Oh, 100%. All right. So the order of transformations does matter because if you do the wrong order, you're not going to get the correct spot. Now, there are some exceptions to that rule. All right. Like, for example, like if you reflect across the x-axis and then you rotate, or how about this? If you, let's say you rotated 90 degrees and then you rotated 270 degrees, you would end up back where you started. Whereas if you did 270 and 90, same thing, you'll end up back where you started. All right, so there are rare exceptions where that's true, that order does not matter, but for the most part, order does matter. All right, so let's actually take some formalized notes on this. So go to page, pretty sure this is 27. So go to page 27. So, biggest thing with composition of transformations. When you combine two or more transformations to form a new transformation, that's what's called composition of transformations. Now, the reason we do composition of transformations is because when you get to math 3, you will then do composition of functions. All right? So it's kind of like a 2-in-1 function. So learning this notation now will help you when you get to math 3 and you have to turn around, instead of doing it in a geometric perspective, you have to do it in an algebraic perspective. All right? So it can be thought as a sequence of transformations. So the image of the first transformation is used for the pre-image of the second, and so on. All right. So in the following diagram, what rigid motions map A, B, C onto RST? So if I started here, and I don't want specifics, but if I start at the green, how would I get to the white triangle? What do you think I would have to do?
Move it left. Reflect across the axis.
So translate left and reflect across the x-axis. Now, we don't know how far we're translating because we can't see the grid, but that's okay. I just want the generalization. Now, it says that in the above composition, it's translated first and then reflected. So this is one of those rare instances where if you did the other first, like if you reflected first and then translated, you would still end up with the same figure. Mainly because there's no vertical translation as well. All right. So that's where it typically messes up. So like if you have a singular horizontal translation or a singular vertical translation, if you do the other first, like the other transformation first, it'll probably end up being the same shape. Now, This is important. So if anything, this right here is what you really need to pay attention to, because this will come back to haunt you. All right. For a composition of transformations, we use an open circle. All right, so if you see an open circle between two functions, two transformations, that means composition. It means you're doing them in a sequence. But you read it from from right to left. All right. So how many of you know what a manga is? Read it like that. You know, you go from right to left. It's a Japanese comic book. So if you know anything about Japan, their books are backwards. So they read from right to left, not left to right.
Or if anyone here speaks Islamic, they write.
Oh, yeah.
Yeah, that's it. Oh, yeah. All right, so here's the example. Now, typically, these will be written in function notation. All right, so remember, capital T and then two numbers, that's your translation. Where A is your what? Oh, sorry, you can't even see it. That's my bad.
Oh, the right angle.
Where A is your what? That's your horizontal translation. What about B? Vertical. So A is your horizontal, B is your vertical. Reflection. Who remembers what reflection is written as in function notation? What type of R? Small r. Reflection is a small r. And then the subscript is the line that you're reflecting over. So that can be x-axis, y equals x, y equals 2, whatever. All right. Rotation. Big R. Now, sometimes they will tell you what point you're rotating around if they don't think it's the origin. But if they put like a O before they put the degree, that just means rotate around the origin. So this just means, this just means around the origin. And what I say about the degrees? How do I know what direction?
If it's negative, it's clockwise.
Right. If it's negative, it's clockwise. If it's positive, it's counterclockwise, because counterclockwise is the standard in math. Unless specified otherwise, it's usually counterclockwise. What about dilation? We learned this one yesterday. Capital D. What's in the subscript? Or any letter to represent the scale factor. All right. So whatever the scale factor is, that's what's in the subscript. So why this is important? Because if we look at what's highlighted in pink, this symbol right here, that represents the composition. So that symbol represents the composition of transformations. And you read them from right to left. So whatever transformation's on the far right, that's the one you do first. All right. Now, the reason why you read from right to left is because when you get to functions, all right, for example, and again, this is math 3, but at some point in your math career, you will see this. And it is the same thing as doing f of g of x. So if you were doing an evaluation, like let's say x was 1. All right. What that means is that you would evaluate your function at g when x is equal to 1. Whatever value you get for that, then you plug that value into f. All right. So that's why you read from right to left. It's more so, like, remember how I said it'll transfer over the functions? That's why. Because typically with functions, the one you want on the inside, you're on the right. All right? So that's the connection of why we have to read from right to left. Because they already made this up with functions, so they're like, okay, since we already did this with functions, if we're going to do the same thing with transformations, we got to keep it consistent. All right? Does that make sense? Kind of, sort of, maybe? All right. So, state the coordinates of the point after the indicated composition. So the point that they're talking about is the point 4, 2. So if I'm looking at this composition next to it, what do I do first? Translate it what? Right 2 down 3. So how do I do that in terms of math? X plus 2, y minus 3. So what's 4 plus 2? 6. What's negative? Or sorry, what's 2 minus? Guys, hush. What's 2 minus 3? Negative 1. Then what do we do? We'll flip it over the x-axis. And what's the only thing I got to do for that? Change the y value to be positive. That would be our final point. Say that one more time. X-axis. So remember, when I swear to God, y'all will stop talking. So when you're flipping over the x-axis, so like for example, let's just say I had a random point just here. So that's 3, negative 1. So all you would do is change the y value, because remember, if you're flipping over the x-axis, you just count the distance from the x-axis. You do the same on the other side. So that would be 3, positive 1. So in reality, the x's, because you're flipping it over the x-axis, would remain the same. The only thing that changes is the y value. And since it has to be the same distance, if you think number line wise, the negative would become positive and vice versa. And it's the opposite for if you flip over the y-axis, the x would change. All right. This next one, still using the same point, 4, 2. What's the first thing we're doing? Rotating 90 degrees around the origin. What direction? Counterclockwise. So, what do I have to do to get it? Flip them and make the y negative. Why are we making the y negative? It's going in quadrant 2, and the y value has to be negative. So 90 degrees counterclockwise from quadrant 1 is quadrant 2. So we got to make the y negative, because quadrant 2, the x's are positive, the y's are negative. Mm-hmm. That is true. That is true. That is true. So that is true. The x's are negative, not the y's. So the other way would have been 90 degrees clockwise. So just be careful with that. See, even I mess that up. All right. So just be careful. And again, if it helps, like if this was on your test, just draw the coordinate grid really quickly. Like you're not using it for graphing purposes, but just label it with your quadrants and the type of points you should have in each one. All right, so after we do the rotation, then what do I do? We're going to translate it how? Left 2, up 5. So what am I actually doing to that point? X minus 2 and then y plus 5. So what's negative 2 minus 2? And what's 4 plus 5? 9. There's our new point. All right, take a minute, try number 3 on your own. So try number 3 on your own. Guys, quit the outside chatter. Get your work done. Come on. All right, thumbs up if you're ready. All right, so for letter A, what do you do first? Reflects it over the y-axis. So what was your new point? -4, 2. Then you would do the translation, and what would you do for that? Add 1, add 4, so your new point is? -3, 6. For the second one, all right, what'd you do first? Add the 1 and the 4, so what would your new point be? 5, 6. Then what do you do? Reflect over y-axis. And it would be -5, 6. So here's the question. Were they equivalent? No. So like I said earlier when we did the first activity, order does matter. All right, there are very few instances where if you flip-flop the order, you would get the exact same figure that you're supposed to get. Very, very few instances where that happens. All right, so composition of transformations is not commutative. Vocab word, what does commutative mean?
You can flip it and it'll be the same.
Right, if you switch the order, it'll be the same outcome. What two operations are commutative? Multiplication and addition. Good. All right. So, let's look at this next one. So, without even thinking about it, all right, rotations. So, let's do this next one together. So, for letter A, we rotate 180 degrees first. So, what will the first point be?
-4, -2.
How'd you know that?
Because it goes into the negative.
Right, so it would go in quadrant 3, and by then we've gone 2 sets of 90 degrees. So if you go one set 90 degrees, that's yx. Second one is xy again. And then you'll change the size of it, the quadrant. Now, if we go another 90, what would that be? Two, -4. So if we go another 90 from quadrant 3, it goes to quadrant 4. So the x has to be positive, y has to be negative, and you have to flip x and y. What about if we just go straight 270 all the way around? Still 2, -4. So are they equivalent? Yeah. So this is one of those rare instances. Okay. So this is one of those special cases. So a composition of two rotations about the same center of rotation can be represented as a single rotation, and it's the sum of the two rotations. All right, so this is one of those special cases for compositions. If you do a composition of two rotations, you can write it as a single rotation if you just add the degree measures. All right. Now, if we look at this diagram, the following composition is represented in the diagram below. So what they do first? They reflected over y equals 4 first. What do they do second? They reflected over y equals -2. So this was the image they got after they reflected the first time. This is the image they got after they reflected the second time. Here's my question. How could I write this as a single transformation? So if I cut out the middleman, if I just go straight from 0 to 2. So if I cut out this step right here, how can I go from here to here in one transformation? Carson.
Wouldn't you just, can't you just like, where it says like T6 to 3, what's it called? What's that part called?
Translation?
Translation. Didn't you multiply those little numbers by 2?
Not necessarily, but you're on the right track with translation. All right, Colden, what do you think?
I don't know, like y1 or something like that. It's like across the y-axis.
So it wouldn't
Or the
be
x-axis.
it wouldn't be a reflection just because they're still orientated the same way.
Just translate twice.
You just translate, but we can only translate once. So Abe, what do you think?
X minus 9.
Right. So if you can just count, let's just say from B. If you go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. All right. You still were on the right track. So if you just go down 12 units, that would be your new transformation. So how would I write that in function notation? So if we do a translation, how would I write that in function notation? Okay. 0, -12. So there's no horizontal, but we're going down 12. How would I write that in arrow notation? Riley. X, y minus 12. X doesn't change, but the y certainly do. Now, what do you notice about the two lines of reflection? So y equals 4 and y equals 2. What's true about them? They're parallel to each other. So another special case is a composition of reflections over two parallel lines is the same thing as a singular translation. So if you do two reflections over parallel lines, so like x equals 1, x equals 3, those are parallel. Y equals -2, y equals 4, parallel. Y equals x plus 2, parallel. All right, as long as they're parallel and you reflect over them in a composition manner, the same thing as just doing a translation. Yes, ma'am? Yeah. All right. What about here? So what they do first? Translate how? So they went right 6 and up 3. So this is where they started. So let's call that 0. That's ground 0 right there. So this is where they end up first. What do they do second? So right 5 and down 4. So they ended up here. Oh, why did I put 3? That's a 2. Now, here's my question. Is there a way I can get from 0 to 2 in one move? How? Eisen. Right, you go T11. So 1, 2, 3. Yeah, 11. And then -1. Because you go to the right 11 and then down 1. So that's how you would do it in one transformation. So T11 -1. Arrow notation, how would you write it? Fisher.
X plus 11, Y minus 1.
Good. So another special case, a composition of 2 or more translations can be rewritten as a single translation, which that makes sense. If you have 2 translations and you do them, obviously you can do it as one translation. It doesn't even change the orientation originally. Now, here's some other ones that we're not going to necessarily test. A composition of reflections over 2 intersecting lines is equivalent to a rotation. All right, so what that means is, let's say, for example, just for an example, and you can write this down on your paper if you want to, but you don't have to. Let's say that I did this composition. So let's say R x equals 2, and then R y equals 1. And let's say I just did it to a singular point. So let's say that point was 4, 5. So lines of reflection first. So my first line of reflection, what's my first line of reflection that I'll do? Oh, y equals 1. So is that a horizontal or vertical line? Horizontal. So then I have the point 4, and then 1, 2, 3, 4, 5. So if I reflect over this line, this is the point 4, 5. That's my original. I'm just going to put a little O up here. Where would it go? So you go down 1, 2, 3, 4 till you get to the lines. You're going to go 4 on the other side. So 1, 2, 3, 4, 5. So it would be 4, -4. That's your first transformation. Then I go over the line x equals 2.
Isn't it 1 over?
I did do 1 over. It's still 4, -4 though. Still the same point though. I just cracked it wrong. All right. So what's my next line of reflection that I gotta do? X equals 2, and is that vertical or horizontal? Vertical. So 2 away, so I go 2 on the other side. All right.
Isn't it 4 -3?
Wait, why did you go with? Why did you only use the 4, 5, 1 of them?
Because that's our original point. So I went down 4, so I have to go down 1, 2, 3. Oh crap! Yeah. My bad. This just goes up 1. So this is the point 0, -3. Now, it doesn't look like a reflection, or not reflection, a rotation. However, However, that's just because the center point is not the origin. What do you think the center point of this rotation will be?
Where the two lines intersect.
Where the two lines intersect. All right. So this would actually be, to get from here to here, you would actually rotate 180 degrees counterclockwise. All right. Yes. Yes. Yes.
What do you use like 4 and 5 for?
I just made up a
That's
point.
the starting point.
I just made up a starting point. So I literally just made this up. All right. So another thing to note is that the center of rotation will be the point at which the two lines intersect. All right. Now, a glide reflection is a composition transformation in which the figure is reflected in a line and is then translated parallel to the reflecting line. So what does that look like? Let's say that my line of reflection. So line reflection is a composite transformation in which a figure is reflected in a line and is then translated parallel to that reflecting line. So let's say I did. So you have to do your translation first, and then your reflection. And let's say that I did it over y equals 4. And then let's say that my reflection would be at zero, 2. All right. So let me just pick a point. So let's do 1, 5. All right. So here's my line of reflection at y equals 4. And then I'll go up to 1, 5. This is my original point. I reflected over y equals 4. This is 1, 3. Now, what am I doing translation-wise? It's down, how many?
No, it's saying like
No, isn't it up
5 is.
It's up 2. All right. Oh. Let's do up 3 then. Again, I pulled these points out of my butt. I didn't think it would, So if I go up 3, this is my final point.
Wait, isn't that perpendicular and not parallel?
Yeah, that's true. See, this is why I don't pull these things out of my butt. This is what happens to me. All right. But anyway, you guys get the picture, right? So
I definitely.
basically, if you're reflecting over this line, you reflect at this point, it'll be over here. If I translated parallel to this line, all right, that means my vector is going parallel to this line. So my vector would be going this way. All right. It would still be. All right, that's what that means. That's a glide reflection. Lastly, any translation or rotation can be expressed as a composition of two reflections. So if you do any translation and then a rotation, it can be expressed as a composition of two reflections. So I'm not going to make up an example for that one because the reflection lines can be slanted, they can be vertical, they can be horizontal. All right, just know that if you do a translation or a rotation as a composition, you can do two reflections on it. Okay, so again, these special cases, you're not going to really be tested on. I'm more concerned of can you read a composition and perform it. All right, but just know that those special cases, they do happen. That's the main thing, yes.
Will the terms be on the test, or is it just like if we can do it?
Say it one more time.
Will the terms be on the test, or are you just testing if we can do the math?
Just the math. Like, I'm not going to ask about glide reflections and anything like that. This is more so of, oh, fun fact, here you go. These are special cases. Yeah, because you really won't see these, to be perfectly honest, you really won't see these much, at least in any of your future maths. You may see them in college, but. Yeah. All right, so for the rest of class, you guys got a solid 30 minutes. Your assignment for tonight is you have a new Delta Math. It's a 1.6 Delta Math. You also have a Unit 1 review Delta Math. So here's how I do reviews. And the reason I'm assigning this Delta Math is I'm pretty darn sure we're going to be out Monday. All right? So, neither one of them are long. All right. When I made them, they said like it should take you on average 30 minutes. On average. Okay. But I said on average. And that's whatever algorithm Delta Math uses to make it. All right. So here's the thing. The paper review that I gave you yesterday, while it's a good thing to still work through it, I'm not taking it for a grade. The Unit 1 review Delta Math, that is a grade. All right. But if it's like one of those things next week where we're just sitting around and you don't have much to do, work through the reviews because that will be on your test. So when we come back, depending on when we come back, it may be we either go straight into your test or we get a review date. Depends on how soon we come back. All right. So if like we're out all next week, as soon as you come back, you'll probably have a test. All right. So I'm just warning you now just to be prepared. Okay. Everyone understand what they're doing? Yes.
Did you say both of these were due tonight?
No. So I made the 1.6 due Monday by midnight. I made the Unit 1 review Tuesday by midnight. So even if we do come back by, because I typically, if you ever want to know when I make a Delta Math due, I usually do the next school day after I assign it by midnight. All right, so you guys got plenty to do, so go ahead and get to work.